Assalamualaikum warahmatullahi ta'ala wabarakatuh. Hi guys, we are from Group 4 and we would like to present our video which entitled Scanning Tunneling Microscope. First, let me introduce our group members, Daus, Zai, Ajira, Shahim and Mirazati.
So, let's move on to the first subtopic, which is about the background of scanning tunneling microscope or STM. What is STM? STM used an analytical technique that is commonly used for biological and nanoscale applications, and it has been used for imaging surfaces at the atomic level. STM is based on the concept of quantum tunneling, which relies on the wave-like properties of electrons. Further details of STM, it is the first member of scanning probe microscope family, which was developed in 1982 by Church Binning and Heinrich Rohrer at IBM in Zurich, created the ideas of STM. Both of the two people won 1986 Nobel Prize in Physics for their brilliant invention.
Next, what is the quantum tunneling? Tunneling is based on the quantum wave-like properties of an electron and will only occur if the barrier, usually a vacuum, is small enough. There must also be an electrical bias, which is voltage different on either side of the barrier to allow for net current flow.
There are 5 basic components of STM, which are metal tip, piezoelectric scanner, current amplifier, bipotentiostat, feedback loop current. In the scanning tunneling microscope, the sample is scanned by a very fine metallic tip. The scanning can be controlled in 3D by a piezo scanner, either bound to the tip or attached under the sample stage. The sample is positively or negatively biased so that a small current, the tunneling current, flows if the tip is in close proximity to the sample. This feeble tunneling current is amplified and measured. With the help of the tunneling current, the feedback electronic keeps the distance between tip and sample constant. If the tunneling current exceeds its present value, the distance between the tip and sample is increased. If it falls below this value, the feedback decreases this distance. The tip is scanned line by line above the sample surface following the topography of the sample.
There are two types of mode operation in STM. The first mode is the constant current mode, which imagines the surface topography at atomic resolution if the surface is composed of the same atoms. The tip's height is measured and recorded, producing an image of the sample surface. Feedback loops are used to measure current and adjust the height accordingly. The tip will move over the sample as the distance between the sample and the tip decreases while the current increases. The tip will then adjust its position to keep the current constant.
The second method is the constant height mode, which imaging the different surface atoms due to their different work functions, which revealing the surface composition or defects. The voltage is measured and recorded, producing an image of the sample surface. Feedback loops are used to measure current and adjust the applied voltage accordingly. The tip does not change in elevation. As the distance between the tip and the sample decreases, the applied voltage will decrease in order to maintain constant current.
Next is the factors affecting the resolution. One of the factors affecting resolution is corrugation. For example, how much the electron density of surface atoms varies in height above the surface. Graphite has a large corrugation and is very planar, and thus is one of the easiest materials to image with atomic resolution. STM does not probe the nuclear position directly, but rather it is a probe of the electron density, so STM image do not always show the position of the atoms. STM imaging depends on the nature of the surface and the magnitude and sign of the tunneling current. For example, if you have copper and silicon on the same surface under the same condition, the current with copper is much higher.
Okay, that's all from us. If you got any question, you can ask Dr. Dalman for better explanation. Okay, bye.